you see my slides?
Yes, we can see our slides.
Okay, wonderful. Okay. Okay, thank you very much for your kind introduction. And also let me thank organizer for giving me this opportunity to talk about some of our recent work. So primarily my talk will be focused on redox flow batteries. In next half an hour, I will be talking about mainly about redox flow battery and what is our interest in this area and why we think it's important, frontiers to in the area of energy storage. So just to start and pitch in the problem, let's look at what are the major, climate change, as you all know, is one of the most challenging problem ever faced by humanity. And there are, it's a sort of a problem where you need a multi disciplines to address this very, very important problem. And it is at the moment, the time is, we do not have much of a time to address this important problem. You see, there is there is a temperature change in a planet, and this is clearly observed. What is the temperature change in the last 50 years? And we have now come to the stage where we cannot afford to change in a temperature of the planet. That plus 1.5 degree, that's a magic number, and we have to really sort of limit the temperature. And this is the major challenge for scientific fraternity, where we have to really address these questions. So you see that it is indeed now we have, this is no more as science fantasy. It is already, people have observed some of the dramatic change, something called climate change induced famine. This is in Madagascar. You see they cannot grow any more plant. Now they eat insects, essentially. So this is something which is need to be addressed. But some good news. The good news is the world leaders have come together, and there is indeed a lot of research interest, not only at a fundamental level in academic institute, but however overall there is a global drive how to control the temperature of the planet and this climate change. So this is something called Paris Climate Agreement, where there are a large number of countries that are part of it. They have signed this, they have pledged rather, saying that we will indeed control the temperature by, sort of with some on mission mode, with the clear roadmap. How are we going to address the problem? And India has, as a country, I'm very happy to show that here, it has shown a remarkable leadership in this kind of this mission. This is some in a Glasgow in a COP26, our Prime Minister talking along with the world leaders. And India has rather pledged, saying that we will put our resources together at different level to address these questions, and how are we going to achieve the net zero. So this is the broader picture for my talk, but I will be talking about a small portion of this issue, but achieving net zero, why the battery research is important, and why the energy storage is indeed an important area of research. So let's take one example now, decarbonization of electric sector. So these are the numbers you need. This is itself is a massive challenge. How are we really going to decarbonize electric sector? If I take one area of to achieve the net zero. So this is the way the cost increases for electrification. And you see the battery chemistry over the years. I'm a chemist by training. I would be rather interested to looking at the chemistry of the battery. Battery chemistry has evolved over the years from lead acid battery to now people are talking about future batteries. This is the lithium ion battery, which is now making a big penetration in the market, but lithium organic is the future batteries. So lead acid battery is the sort of a old, battery, which was developed in 1859 and currently dominates the market in a different way. It's a very robust battery. If I sort of draw a similarity between a battery research and solar cells, this is like a silicon solar cells. In a silicon solar cells with a very robust, in terms of lifetime. But lead acid battery is also very robust, but it has its own limitation. It cannot have a very high in energy and power density. It is a sort of a heavy battery, and it is use acid. You also use a toxic element like a lead. But however, there are now methods to how to recycle these issues. So lead acid is indeed the dominating technology currently available in the market. But now we need to. It's important we invest the time and energy to develop new class of battery to come over some of the limitations in lead acid battery. So lithium ion is the battery, which I'll little bit talk about in the next slide, is indeed a battery which is now making a sort of a penetration in the market, as I said in the before. But now future of the battery lies here in lithium organic. Actually, how are we really going to make it a sustainable battery solution actually to achieve the net zero? So there are other kinds of battery, nickel cadmium, nickel, and the lithium ion based on a high, lithium air. There are a range of batteries have been recently, people are pursuing the research. So let's take an example of a lithium ion battery now. Suppose if you really want to decarbonize the electric sector, this is indeed not the solution, because lithium battery contains these electrode materials. For example, you have a cathode and anode where we have a graphite and we have some inorganic, a complex inorganic compounds. And those compounds are indeed going to pose a lot of problem, because it is also, if you start decarbonize in a large scale, this battery is going to really create environmental risk along with addressing the problem of a decarbonization. It is very difficult to recycle these batteries. It's very expensive. It's not also safe. I think there are like many, but then it cannot be also used for bigger storage, like a grid storage application, bigger plant. It will work for a computer's, cell phone. I think Tesla has introduced the car, but these are the sort of globally introducing such car is indeed very, very challenging. And lithium availability is also dominated in certain aspect of the continent. It's not everywhere. Lithium is available equally. So we need to really think about cheaper and safer and high density battery, which are abundant, available across the globe. And we need to really address those questions. One of the area which we currently interested in our group also is, can we use organic electrode instead of inorganic material? Can you use inorganic organic electrode material which can be recycled? Okay, and then create a cheaper and safe and high density battery. So, but today I'm not going to talk about this class of a battery. I'm going to talk about a redox flow battery. So let's look at why redox flow battery. Now, redox flow battery is indeed very, very interesting class of a battery. So what this has, I have shown here is a discharge time at a rated power versus a system power rating. When you go in a higher and higher in terms of energy storage, when you go for a higher module, indeed you need a different class of battery. Lithium is not going to serve the purpose here. For example, this lead acid battery, or if you go to a 10 megawatt plant actually for energy storage, you have to really think about beyond lithium. Lithium is not going to really serve the purpose, but as good as lead acid battery, flow batteries are indeed a very useful candidate for such a large storage battery. So in terms of applications, it has a large number of applications, especially for a grid storage. As I said, it is one of the beauty of this battery is the power and energy density are decoupled. Actually, you can independently scale up power and energy, because you are here, what in a typical redox flow battery, what you do is you store a catholyte and anolyte in an external reservoir, and you have a stacks of electrode placed in this one. What you do is the way you use a pump to circulate these electrolytes in those stacks, so you can independently couple power and energy density, unlike other batteries. For example, lithium battery, you cannot independently decouple power and energy density. But whereas in redox flow battery, you can independently play with the concentration of electrolyte, you can play the solubility of the electrolyte, and you can also play with the number of stacks. So these are all decoupled. That's the beauty of this battery. You can also do deep discharge, and it can be operated at room temperature. It can also, if you are having, if you take some safety precautions, especially for aqueous redox flow battery, I'm going to talk about, there's not much of a safety related issues. When you go for a non-aqueous flow battery, of course, one has to be very careful about the safety part. But today I'm going to discuss only, most of my talk will be focused on a aqueous part of the battery. So there are different kinds of battery. I will not spend much of a time again to introduce you. The redox flow battery can be all liquid phase, like a vanadium flow battery. It can be a hybrid, and it can be also all solid phase. So these are the class of battery, depend upon what kind of material you use in battery. Based on that, there are different class of, they have been distinguished on a different based on the kind of material you use it. So let's compare now aqueous versus non-aqueous. If you ask me this question, which is the better one, aqueous versus non-aqueous battery? If you look at the main major advantage of the aqueous electrolyte is basically this is very cost effective, very cheap. Actually, you can do it with the and then you can demonstrate at pilot scale. People have demonstrated already at pilot scale, but it has a very limited narrow window. You see that this is what beyond this window, if you go, you see this hydrogen and oxygen evolution, which is not good for a battery. So essentially what the window is very limited, up to 1.5 volt, and it has also limited temperature range. You cannot go, let's say, for example, if you go a freezing temperature at very cold part of the continent, then what happens is liquid electrolyte can get also frozen, and then you will have a difficulty of operating those battery at those temperature. There are also very limited redox couples in this aqueous batteries. Currently, people are using vanadium here. You see it exists in a different oxidation state, whereas it has very limited window. And then people have already demonstrated, as I mentioned, vanadium battery has been already demonstrated at pilot scale. And the beauty of this one is the safety. It's a non-flammable aqueous solution. You can use it. Now let's compare this part with the aqueous flow battery. Non-aqueous flow battery. Non-aqueous flow battery has comes with a lot of several different advantage. Non-aqueous electrolyte have a wider electrochemical stable voltage. You can play a redox, a potential of these all organic material by functionalizing these organic material with the different functional groups, or modifying the donor acceptor backbone. Here you can really play with the redox window. So based on the nature of this backbone in the here, you can really go from a very high stable window up to 5 volt. And then it's a problem is also, you can use some of the solvent which are in extreme climates. These solvents, it seems to be astronitrile or DMF, they are stable. It has a great diversity, tunable chemical structures, and also cost is still an open question because these batteries are not yet scaled up. So cost is indeed still very, it is too early to talk about the cost, but when you scale up, the cost may eventually come down. And there are large number of redox couples. Organic chemists have introduced a variety of all the heterocycles already available in the literature. One can play with these things and you can scale up and you can make it a battery at a very high voltage Windows battery. So these are the two advantages. So in our group, we work on both. Then I will show you one of the aqueous as well as non-aqueous. Our research efforts are actually, we work in both the areas. So one of the challenge when we started working in this area, the stability region, stability, electrochemical stability window, we talked about it. What is the position of these energy levels? The redox couple should have a LUMO deeper than 3.5 EV with respect to iron HOMO has to be below these voltages, but what happens when you go beyond these voltages? For example, you have competitive reactions when you have water and when you react with this one, when you reduce the electrolyte and then you generate hydrogen and hydroxy ion. Similarly, when you oxidize, you have reactions with oxygen. So it's important we generate new materials. As I said, we have a large number of variety of materials, but however, the material needs to meet this criteria of a stability window. So we recently worked on a variety of a donor acceptor polymer. You see that in our group, we have been working on this donor. It's a thiophene and the DPP lactam ring as an acceptor. Then we have these donor acceptor structures. We can play with this window. We can change from thiophene to pyridine to selenium, and you can also introduce these nitrile groups. So, and you can introduce a variety of different alkyl chains on this nitrogen. So why we believe this one? This is something exciting because we have a handle in a same molecule. You can go with the redox couple from from a very wide range of potential window we can cover by playing with the functionality. So we synthesize the material. In one of the material we synthesize in our lab is going from this thiophene to nitrile thiophene to achieve the LUMO, the lowest occupied molecular orbital below -4 eV. By doing that, what did we achieve? Our challenge was very high electron affinity. It can easily reduced. Okay, it has a deep LUMO level, and when you expose to the air, it is a very stable analyte actually. So that's a challenge in the field. There are not many analytes have been introduced so far in the field which are stable at ambient condition. So this is the challenge we took up in our project, and we developed this DPP nitrile. First, we did the cyclic voltammetry of a very different class of different materials, and to find out where do they oxidize and what is the nature of this redox couple. Electrochemical potentials were analyzed based on this one. For example, thiophene DPP does not really give a very reversible cycle, and then pyridine DPP, it gives some sort of oxidation, but they are also not very stable and reversible. However, when you go to the nitrile, we clearly see a beautiful two peaks which are reversible in nature. For example, when you go to selenium DPP nitrile as well as this thiophene nitrile, we do see a very nice reversible peak coming in. So indeed, this means this is the first lesson we learned by doing this experiment. We know the nature of the backbone is very, very important. It is indeed electron affinity of these materials decides how easily these analytes can be reduced. So we could learn these lessons from based on that, and then we discarded these materials. These are not, turns out to be very good material for flow battery applications. We focus our effort on these nitrile to take it forward to study more. So this is what we did. This is our battery, what we built. We have an analyte side where we took this nitrile and we use different catholyte. We use initial blue, DBBB. These are the very simple available in you can purchase these catholyte. And then we have a 2-electron discharge process for example, initial blue. And our material also has a 2-electron charge discharge based on the cyclic voltammetry I showed you previously. So we compared the results now. We took analyte and catholyte along with this different tank, and we used some ion exchange membrane, and we built a battery to study the utility of these DPP material as an analyte in these class of material. Here is again, we use a different salt. It's important again, which is giving a best results. This is something, a basic fundamental science. One has to screen out a different class of a salt. For example, TBAPF6, it shows a very reversible CV. When you go to sodium triplet, this did not show very reversible, whereas lithium TFSI indeed show very reversible. What this essentially tells me is, essentially, if you want to draw the conclusion from this, it's a sort of ion dependence. You see that the electrochemical behavior of these particular material is depend upon what kind of salts you deploy to do a redox reactions. So we could do very good reversible. There are a large number of multiple cycles we did it by using TBAPF6, and indeed we found this material is very, very stable material. But however, when you go for a sodium triplet and other lithium TFSI, particular sodium triplet, we did not find a very stable electrochemical potential in this class of material. So we stick with that, I think TBAPF6, and then this is all again cyclic voltammetry of a catholyte. We choose, this is unicell blue, and then we have this DBB material. Now what I've done is I compare here. So this is 2-electron here, very clearly reversible, very nice cyclic voltagram. And now I compare here. I use initial blue and nitrile. I can see that I can theoretically, I can build a battery in a range of 1.26 to 1.4. Depends upon whether I use a selenium or a thiophene hexyl nitrile. Depends upon what kind of catholyte I use. I can make a non-aqueous flow battery for this potential window. So this is a lesson we learned by doing this basic electrochemical characterization. We can indeed build such a battery. So this is our cell. Again, I will not spend much of a time, but it contains all the necessary component to build a redox flow battery. It has a stainless steel plate, O-ring, carbon felt, and then we use Nafion 117 as a membrane, and we use these catholyte and analyte to build the battery. So we built a battery and we characterize here. So interestingly, what we see here. So this is again more like a crowded data where you see that when you did a cycle up to 100, as a percentage of the capacity versus cycle, when you screen out, the capacity indeed faded away for a 100 cycle, close to. So, and then, but our Coulombic efficiency was not that, degraded as compared to this capacity when you did compare with the cycle number. And then this is charge discharge capacity for a different material, where here we take UB-TDPP hexyl CN4, which we developed in our lab and built a cycle. So what we see here is indeed when we characterize this battery at room temperature, we see that as a function of a time or a function of a discharge density, indeed the capacity fades lower and lower. But we could go to up to 100 cycle. So then, based on that, we did some single cell studies to identify, to understand why there is a degradation or why there is a sort of the battery capacity fades away as we increase number of cycles. So we did a single cell studies here, and then we did the charge discharge cycling for using both side a material, the similar material here, and then we did a more detailed study about to understand the charge discharge cycle. So here is the data for that one. We indeed see that this on UV symmetric flow cell. Actually, if you look at this one, this is a flow cell from using the material we developed in our lab. Indeed, it shows a very stable up to a large number of cycles. But when you have this Unisol blue as a catholyte, which we purchased and used it, that did not have a very stable capacity. So our anolyte is extra stable. As considering the LUMO level of this anolyte, we could go up to 700 cycles and make it like very, very stable anolyte. But whereas, however, when this anolyte, when in oxidized form, indeed the capacity fades away. And then what lesson we learned is our idea of a chemistry to rationally design these anolyte worked very well, and we could identify from this work a very stable. And then again, we did a very, very detailed analysis on this one, which one really indeed, this is the optical piece. Yeah. Hello? Someone talking in between? Is there anything? Sorry.
The time is 2 minutes left for your presentation.
How much? Sorry, I can't hear you.
2 minutes. 2 minutes.
Oh, okay. All right. Okay.
Fine. Thank you. Please.
Okay, fine. Okay, so this is what we did, and then finally, this is what we concluded. What we did here is indeed we developed a new class of a anolyte material, and which is a sort of a proof of a concept flow cell. We made it by using this Unisol blue and DBB. And then we have a sort of what we compare the capacity of or stability of this anolyte, and indeed it shows a very, very stable system in a flow battery. So symmetric flow study shows that stable capacity behavior over 700 cycles, and UV visible absorption study shows that this TDPP hexyl is a stable anolyte for Redox flow battery application. So this is where I did a little bit, just finally I talk about it. This is the last sort of 1 or 2 slides. I talk about the soluble Redox flow battery. In this area, what we do, we try to make use of this lead methane sulfonate as an electrolyte. What we have is we do not have a membrane. This is rather a simple battery. The beauty of this battery is there is no membrane, and we dissolve this electrolyte in this reservoir, and then we use here single electrolyte, no membrane, low cost active materials, and widely abundant. So, but there were initially we had a lot of challenges to address, and we had lead dendrite formation, oxygen evolution, lead oxide sludge. So we address all these questions, and perhaps I can go to my a last slide, talk about. Okay, so currently we stand here with this slide. I can stop my presentation. What we did here is we started a single cell studies in 2016. Now currently we have 8 cell stack soluble lead redox flow battery, and we address each and every question. And this is where currently we stand with the a sort of a stack of a soluble lead redox flow battery, which has, this is a video which talked about, you see, this is the way my students in the laboratory they are stacking these cells. So we have made a 250 watt hour a module in the lab by using soluble lead redox flow battery by using this. This is the way the stack looks, and then you can see this is currently working in the lab. So now the idea is we are taking it forward to make it a 1 kilowatt cell. So I showed two aspects. One is aspect is basically talked about non-aqueous redox flow battery, where there are challenges to develop these stable catholyte anolite. Those are at very small scale, but insoluble lead redox flow battery, which is more cost effective and aqueous, where we can go up to, we can, demonstrate a sort of a product at a TRL level 3 to 4. So with this, thank you very much. I think these are the collaborators and students, worked on this project. I'm grateful to them, and I'll be happy to answer any questions.